Hi, everyone. I'm Marcel Verona, Digital Marketing Manager with Move Media, and I'd like to welcome you to this session. Please remember that we'll be recording this and it'll be available to watch on demand afterwards. If you have any questions during the session, please add them to the Q&A on the right-hand side. Your questions will be sent privately. So with that, I'd like to introduce our speaker. I'd like to welcome Kai Schlüter, sales engineer at Jungheinrich, who will be speaking about the pros and cons of fully integrated powertrain systems versus individual component picking. Thanks for being here today, Kai. Please go ahead.
Thank you. Yeah, thank you very much for the quick introduction. Hello, also from my side. As already told, I'm Kai Schlüter, working as a sales engineer at Jungheinrich, specifically at the Jungheinrich Powertrain Solutions department. And to give you a quick glimpse of what we do as Jungheinrich and also why I'm now speaking here on this conference, I would like to lose some words about Jungheinrich itself as a group, and then also Jungheinrich Powertrain Solutions. What do we do, and where does our knowledge come from that we think that we can have a talk here? Maybe as a quick disclaimer, even before that, if you have any questions, please put them in the Q&A section. It would be really great to have some thought exchange after the presentation. I don't really want to talk like 1 hour through and then everybody just leaves. I think the talk will be much shorter, but I would really like to go into discussion afterwards if possible. Starting with facts and figures about Jungheinrich itself. Many of us, or many of you, might know Jungheinrich from their forklift truck branch. So everything that runs in a warehouse or even is a warehouse is also supported by Jungheinrich. In 2023, we looked at a revenue of 5.5 billion euros, have now more than 21,000 employees worldwide in 42 countries. And I said that in the warehouse, many things are from Jungheinrich, and most of the forklift trucks are from Jungheinrich as well. And we are currently looking at an active fleet of more than 1 million electric forklift trucks that are in use worldwide. And to be able to service all those forklift trucks, we have more than 6,000 service technicians, really technicians working after sales business, plus I think like 1,500 people as an overhead administrative part. So in total, more than 7,000 people working in after sales and servicing the whole fleet. In regards to general portfolio, if you need anything for your warehouse, or you want to build a warehouse, or you want to equip your warehouse with anything that you might need, give us a call. I think that we might have it. But the most important thing here on the right-hand corner, maybe I can even have a laser pointer here, there, is that Powertrain Solutions is, as a department, is one part of the whole Jungheinrich portfolio, next to the customized trucks, small series trucks that we built in Lüneburg. It's our plant for special builds, where we build small production lineups up to 5,000 machines per year, or also one-off machines if the customer requires a very special build for one special application. This is where our expertise comes then also into play, to develop that machine for him. I said that we are active in more than 42 countries, and by active, I mean that we have direct sales, direct sales branches in each country, meaning that we are really with Jungheinrich employees within this country. And in every country that we have a sales branch, we also do have our after sales technicians. And so everybody likes to have a view of the map of the world and paint everything in their color. We do that as well, obviously, but I think this is or if you have a Jungheinrich component, for example, a battery, the service network is there to service any kind of components or machines sold by us. Now, speaking about Powertrain Solutions as a department, It is important to know that we started in 1953 with the first, with our first machine here. On the left-hand side, this is Dr. Jungheinrich, our founder. On the right-hand side, we we still to this day we don't know who it is, but the most important thing here on this picture really is the Ameise 55, which was the first forklift truck that Jungheinrich brought into the market, and this one was already fully electric. So in 1953, fully electric machine, lead acid based, obviously, but as you can imagine, back then it was quite difficult to find suppliers who have batteries, who have chargers, who have inverters, who have the know-how to build up an electric powertrain. And the decision of Dr. Jungheinrich was, well, then I might just do it on my own. And from that day on, the most components of the electric powertrains that are used in our machines are produced by us within our own facilities, designed by us, then produced, then serviced afterwards. So this is a real good integration that we're looking at. And we therefore had the option to always be at the forefront in terms of electric machine development and also general electrification of movement. And therefore, in 2011, next important step here, at least for the Powertrain Solutions department, was the introduction of lithium-ion technology into forklift trucks, which then gave us the opportunity to say, okay, the energy density is that much better than with lead acid. We now also have components that might be interesting for other customers as well. When I say that we produce the things ourselves, we mainly produce the most of the components in Germany, actually, and in Norderstedt specifically, which is more or less Hamburg. It's on the northern side of Hamburg, but it's really you drive out of Hamburg and then you drive into Norderstedt, where we have a factory only for our traction and drive components, meaning inverters, meaning motors, meaning wiring harnesses, PCB assembly, batteries, everything you can imagine of a electric powertrain. And the current, let's say, the current numbers are that, for example, last year we produced more than 500,000 PCBs on our own, more than 200,000 inverters, 60,000 chargers, because obviously we produce more than 100,000 machines per year, and then you have 1 or 2 or 3 inverters. If it's a single inverter in one machine, then you also need some numbers of inverters. And now also, this is what we can see here is the population of lithium-ion batteries that we brought into the field. And what we can see is that in 2011, that was somewhere over here, we introduced them, and then nothing happened. And at some point, big customers like Lidl, Walmart, or others, IKEA, for example, they made the calculation for TCO and found out that lithium-ion might be more expensive upfront, but in terms of the TCO calculation, it is much better than any lead acid battery that you might find. And they changed towards lithium ion, and from that day on, it really hit off also in the forklift truck business. And now, bringing all of this together, the expertise from 1953 until now of designing, integrating, producing electric powertrain components, then also having these electric powertrain components available and being able to bring them out to other customers is really what drives the Jungheinrich Powertrain Solutions department. We are, so to say, the interface from our own components towards other customers who want to electrify their machine. We have done quite a lot of projects since or within the last 10 years that we are working as a Powertrain Solutions department, and have started really with wheel loaders and telehandlers. Wheel loaders, for example, the first Kramer electric wheel loader, full electric wheel loader. This was done with us, which was the world's first fully electric wheel loader. And for example, also here the telehandler of JCB is in the field. The wheel loader is a small small, medium wheel loaders of Tobroko Giant. They are also completely equipped with Jungheinrich electric powertrain components. And for wheel loaders and telehandlers, it's quite easy because in the end, they are more or less a forklift truck. They look a bit different, but they lift heavy stuff, bring it from A to B, and drop it down again. So it's almost the same. And telehandlers are even governed under the same regulations and laws. So that was an easy task, low hanging fruit, so to say. But we quickly found out that with the forklift truck components that we can derive directly from our forklift trucks and then use the scale effects that we have in terms of producing 100,000 forklift trucks and bring that into the field. That this is very interesting and also very fitting for various different applications, from rollers to livestock uh, uh, um, mixing and feeding machines towards airport equipment, a variety of different applications, and that makes it really really interesting in the end. Um, I I mean, this slide is a bit might come across a bit cheesy, but we really are proud of it. In the 2025 Interact Analysis of Highway Powertrain report, that gathers the numbers of batteries and motors sold to small of a small and medium size of highway vehicles without the scissor platforms, excluding forklifts and scissors. We are really seen as top of the pack for off-highway batteries. What that means is that we have sold in the last year, in 2023, where these numbers belong to, we sold more than 1,000 batteries into the field, and way more than, I think, 1,500 motors, depending on the machine. So we had a big share there, and since we're looking at 10 years of development phase and projects, that really made sense in the end. But it was great to see. And what we learned along the way is that there are different approaches to approach a electrification project. Either if you want to electrify a already existing diesel machine or any kind of internal combustion engine machine, or if you want to build up a completely new machine and electrify it from the start. And before I jump into the next slides, I also want to give a quick disclaimer that obviously all those information that we gathered and that we put into this presentation and into this talk, they are based on our subjective thoughts, feelings, and what we have learned along the way. Our impressions and all the information that we gathered, they might differ from what you have experienced. This is totally possible, and therefore they can only be seen as our own information and expression of what we think. But we think that this is still interesting and important to speak about. So, starting off with key components and their main interfaces in an electric powertrain system, and I believe that many of you, all of you, are talking more or less about the same four components when thinking of the general most important components of electric powertrain. You have a battery. This is always the main discussion point. Then you have a charger to charge the battery. And then you have an inverter where you get the power from the battery and then transmit it in the end to the 1, 2, 3, depending on the machine, electric motors to drive the machine, to propel it forward, but also to use the working functions, hydraulic working functions. This is what we consider in this talk, at least, as the key components in an electric powertrain. And those key components, they have a lot of different interfaces. Just going through the main important interfaces that we see and that we discuss in every project that we have. Starting on the left-hand side here with the battery, which is usually the most important one. You have a CAN interface towards the machine, so towards the customer, towards the OEM machine, where you transmit informations like the current SOC, the allowed charge and discharge currents, so that the machine can adapt. You might also transmit error codes in terms of, for example, safety situations or safety-related situations, or if a component is really defective. Then in the other direction, you have the CAN interface for the charger, because also this must work together very well in terms of charging, balancing, and then also general current demand in terms of regen, for example. Then you have the electrical interfaces. They may differ from battery to battery. We have screwed poles, for example, on the 48-volt batteries. We have high voltage plugs with interlocks for higher voltage classes, but generally you must have, to some extent, one plus and one minus pole. And then you also have signal interfaces, meaning electrical signal interfaces. For example, for the key switch to boot up the battery, you need some kind of charger detection usually, so that the battery knows that the charger is connected and then it wants to charge. Speaking of the charger, also there you have a CAN interface so that you can receive the current requests of the battery. You have electrical interfaces, also here, plus and minus. You have signal interfaces, as just said, in addition to the CAN. Maybe it's only CAN operated, could also work, but you often also have signal interfaces, for example, for the charger detection. Jumping over to the right, speaking of the inverter, also here, CAN interface, where you receive current speed and torque limits, also the current speed and torque requirements that the machine wants to have. It might also be used as a general CAN network management unit, meaning that it also has a big processor to drive other communication to other components and transmit it as one to the machine. And then you have the electrical interfaces. You have the DC power towards the battery, where you get the power from, and then you have AC power towards the AC motor. And then usually the most easy one is the electric motor, which has electric interface, 3 phases, usually if it's an AC motor. You also have the model for the inverter to be able to drive the motor and to know what kind of motor it is. And then you usually also have temperature and speed sensors within the motor that transmit the current status that it has. And if it wasn't even easy enough or problematic enough, the slide before, when you then connect all of those, there is quite a lot of going on within the machine, even within those 4 single components connected to each other, because it is all one big system. You have a master controller. At least this is how we do it. You usually have a master controller that has one connection or works as one interface towards the OEM machine, usually running on CAN J1939. And then for us, it's an CAN open vehicle bus. All our components are used or are using CAN open messages and CAN open buses from the master controller to the inverters, to the central BMS unit. The BMS then communicates also with the onboard charger. It communicates with the batteries. The batteries communicate with the inverter, and so on and so on. In this case here, as an OEM, you have one interface, meaning you have a, so to say, fully integrated powertrain that is designed to work together and is therefore only communicated or communicating via one interface, and also can be changed, or let's say can be addressed by the OEM machine in an easy way, and manages all of the rest on its own. But then you can also have a a hand-picking approach for those components, meaning that you, for example, have a motor from one supplier, an inverter from another supplier, batteries from a third supplier, and an onboard charger from a fourth supplier to make it plain, and to make it easy. And then you have four different suppliers, four different components that are, for example, for your specific machine, they are fitting mechanically perfectly. They have the perfect energy density right for your application. They're maybe even not only handpicked, but also built to your machine, could also be. And then you don't only have this communication line here, but you also have to some extent, manage all the rest, manage all the communication between these components, not only wire towards a wiring diagram, but also uh, just speaking of different CAN lines. If you're working on CAN open and another component is working on CAN J1939, you also need to have some kind of translations between them. So this is then getting increasingly more difficult in terms of making all these components work together. And to give you an overview of the most critical interfaces that we usually see within the project, the first is very well known, which is the interface between the charger and the battery. Um, we have put some examples here on the slides. There are more things in each interface that needs to be dialed and that needs to work together to get the whole system working. But these are the things that are coming up quite often within a project. First one is activation of the battery by a charger. I said before, there is usually some kind of CAN communication between those components, and then also an electric communication if possible. And if just speaking about the situation that the machine is turned off and also the battery is therefore turned off, and you plug in the charger and you want to charge, then the charger needs to be able to wake the battery, to make it safely, to make it reliable, and then also to start charging. But the charger should not just start charging and the battery sees how it goes. It's rather that the charger should only apply voltage and drive the current towards the battery if the connection is safely established, if the handshake is done, if the battery says or broadcasts the current demand on the CAN bus. So this needs to be dialed. And also balancing after charging. Speaking of lithium-ion batteries in general, but also LFP batteries that we are usually using, you need to have a very good balancing of the battery, of the cells, depending on how the battery is set up. It can be during charging, it can be during charging and discharging, but also, especially for LFP cells, you need a very, very good balancing time frame at the end of charge to be able to really determine that you are now at 100%, and then start the SOC calculation again afterwards to be able to determine the SOC during machine operation. Speaking of the interface between batteries and inverters, the battery broadcasts allowed discharge and charge currents, including the regeneration currents. And if these discharge and charge currents are not obeyed by the inverter, by the rest of the machine, and they overdrive, so to say, the battery in terms of charging too much or also discharging too much, the battery can also protect itself and say, "Oh, look, that was it for me. That was not how I what I said I can do," and switches off if it sees over voltage or over current. And that can really lead to critical vehicle behavior if the allowed discharge and charge currents are not obeyed, but also if the safety functions are not completely done in a good way for such a situation, so that there's no REM stop, but rather a full stop, which can also cause some headaches if you bump your head on the window. And therefore, the power consumption and the regeneration that can be brought back to the battery, they need to be managed on system level, not only between battery and inverter, but also within the whole system. For example, to activate to activate a different brake if the battery says, I'm at 100%, I cannot take any regen anymore, please use different brake. And also power management, meaning that if you have different different motors that you want to drive within a machine, or different courses where you have to distribute your currents, the inverter needs to be able, the whole system needs to be able to determine where is the power really needed at the moment, and to make some trade-off. For example, not going as fast at the same moment when you want to lift, or when you want to lower. It's an easy example, but this also has to be thought of. And then also between inverter and motor, I said it before, you need some kind of motor model that the inverter at least knows which kind of motor it is driving. And to ensure predictable and safe motor operation, because it is quite easy to let a motor drive in the opposite direction than you want it. It's it can happen. And therefore, these models need to be designed and working on the inverter. And then also, speaking of functional safety, I don't want to deep dive too much into that, but the safety of the drive system itself, meaning the machine should only drive if you want to drive it, and also should only drive towards where you want to drive. This also needs to be managed on a system level, but also specifically between inverter and motor, to be able to comply with functional safety requirements. And now, having said that these are, at least in our opinion, the three main critical interfaces, some examples of what can and often might go wrong. Example one, timing and sequence between charger and battery. Because depending on who built the battery, who built the chargers, um, it can happen that what the charger is able to do, to, for example, wake up the battery, or to try to make a handshake in terms of charging afterwards. Many batteries expect a certain sequence of events. For example, that the charger sends a hardware signal, electric signal, to a specific pin on the BMS, and then needs to send heartbeat via CAN in a certain time frame. If that doesn't work, if, for example, either the hardware signal cannot be transmitted, or also the heartbeat comes too late, that might lead to the battery saying, oh, this is an unsafe situation, and going into error state, opening the contactors, and rather protecting itself before there is kind of a safety critical situation. But also waking up a battery from deep sleep. If a lithium-ion battery is discharged too much, and the cell voltages drop under a lower value, under a certain value, then it's often very likely that you cannot recover the cells anymore, and that they are really destroyed, and the battery therefore is also destroyed. And to prevent from that, many batteries have some kind of a deep sleep mode, meaning that they protect itself, shut off all currents that go out of the battery, and only tries to keep the voltage at a level where it's still in a good condition, and then needs to be waked up again by a charger, and then charged directly to get out of this critical cell voltages. And this can be done by connecting a charger, but the question is if the charger and the hardware signal it can send, and the electrical interface is as powerful enough to really wake the BMS to send the currents and the voltage that is required to wake up the battery again. Now, between battery and inverter, very, very important thing, pre-charging. especially inverters with the condensator banks, they can have a very high inrush current, and if these if the contactors are just closed and the current is running over them within the battery, this might lead to the contactors being stuck and cannot open anymore. And therefore, for example, a battery can be equipped with a pre-charge system to charge the capacitors before um, the whole contactor is closed. Or you can also build your own pre-charge within the connection between battery and inverter. But this is always depending on the capacity of the condensators or of the capacitors on the inverter, and also the contactors that are built within the battery. So this needs to be checked and dialed. And then also too much regen. If the inverter just puts too much regen current back to the battery, at some point the battery cannot accept any more charge. It is completely full. Cell voltage is either high, and then the battery opens the contactors to protect itself. And this is then also where the whole system needs to jump in and, for example, break on a different level. Just speaking of somebody charging a machine to 100%, and then the first drive is 5 kilometers downwards from a hill. Sounds a bit weird, but I can tell you, if you don't have thought of such a thing during the development phase, this is definitely the first thing that will happen to your machine if you sell it to the market. This corner case is more common than one might think. And then also between inverter and motor, everybody's talking about efficiency of electric system, and the efficiency really comes down to also the connection between inverter and motor, because only if the motor model is good enough and the inverter can really drive the motor precisely, then you achieve the high efficiencies that a electric powertrain can achieve. And then also the precision, in terms, for example, of lifting a pallet, for example, in a forklift truck. This is also very important. The precision of knowing how the motor is turning, how much it needs to turn to, for example, lift the weight for 1 meter or so. This is really important, and this also makes the operator feeling and the operating experience with the machine very good or very bad if not done correctly. Now, having said all that, jumping into handpicking components in terms of advantages and challenges. Because there's one very, very, very big pro for handpicked components, which is that you can customize every single component exactly to the need of your machine, of your individual packaging and performance requirements. So this is really a pro that no fully integrated system with standard components can reach. You can choose exactly for your needs. You have the freedom of choice from every supplier, from every component, every cell chemistry. Everything is possible. And this is really a pro if it's done correctly. In terms of cons, the entire responsibility for functionality, safety, over reliability of this powertrain system is with the OEM or with the system integrator, depends on who does it. And especially for OEMs starting off with their first electric machines, maybe second electric machine, this experience and the resources in electrifications, they are usually quite limited at that stage. And this can lengthen the time to market. This can also be the root cause of defects. And even if you know that the defect is in some component or in one component, or you say, this was not us, this must be in some component, and we cannot look into the component because it's kind of a black box, for example. Then it gets interesting because just speaking of charger and battery, the battery doesn't close the contactors when you plug in the charger. Then the charger, the supplier of the charger might say, "Oh, look, this is a battery problem." And the battery says, "Oh, no, this is definitely not our problem. This is in the hands of the charger supplier." And then you're getting some kind of pointing going on, and this can lead to difficult solution finding, but also difficult warranty cases in the end if it's in serial production and something comes up, right? In opposition to that, speaking of fully integrated systems, if you have all those 4 components, for example, from one supplier, then it's more clear. If somebody sold you all those 4 components and one of those components isn't working, then you know who to call, and you also know who to force to get it to work. Speaking of time to market, if you're working with powertrain components that are designed to work together, and also in different or in other machines that are tested to work together before they are sold to you, this can really drastically reduce the time to market if they fit in your machine, and therefore they generally offer lower risk, lower cost, usually as well. Hand-picked components are, in comparison to a standard component that is produced on a high scale, it's obvious that they are usually not as costly. But speaking of cons, as I said, pre-developed building blocks, so to say, they really come with a limited choice of form factor and customization because they are standard components designed maybe also for the use in one specific machines, and they are now adapted for your machine. And this leads to, especially in terms of mechanical things, mechanical interfaces, also maybe weight requirements, weight restriction. This might lead to problems in integrating the whole system into your machine, not the system and the components within the system, but the whole system into the machine. This is then a challenge to overcome, usually on a mechanical level. Coming to a conclusion, as I said, this is our experience that we had throughout the project that we have done, that we have known of, that we have heard of. And we think that there are definitely machine types, vehicle types, where handpicking specialty or niche components is really necessary to achieve design targets in terms of packaging, in terms of performance, in terms of USPs, maybe. But also, on the other hand, most vehicles can be equipped with fully integrated powertrain components, standard components that offer then low risk for integration, but without sacrificing the performance and the overall output of the machine. Because what we have experienced is that many OEMs are driven by a mechanical engineering mindset. That means they really try to avoid any kind of mechanical complexities and changes, for example, to the frame, to the gearbox, which is understandable, obviously. And they therefore then handpick components that allow for minimal adjustments of the already existing machine. But then that in turn increases the overall, we call it project risk, but also it increases the complexity of the powertrain system that the OEM has to manage, or the system integrator has to manage, because you have handpicked the components and now have to integrate them on your own. Obviously with help, but still not as easy as a fully integrated one. And therefore, our recommendation in one sentence is always focus on your strength. If you have done mechanical adaptations, development of mechanical or of machine with internal combustion engines, with mechanical adaptations for years by now. Really place your project risks where you can see and manage them, meaning maybe make some adaptations to the mechanical interfaces. If possible, do, for example, a bit of redesigning of the frame, if possible, and then integrate standard components that are really designed to work together as a fully integrated powertrain system and accelerate the development and also lower the risk of the whole project. Which doesn't mean that for the next machine, for example, or the machine after, you can do a completely different approach by handpicking, because you then have built up the experience, for example, and the knowledge to do that. But especially if you're starting with electric machines and transferring from diesel to electric machines, try to place the projects with where you can see and manage them. Yeah, you can still see. If you have any questions afterwards, please reach out in the Q&A system. But also after the presentation here, after the talk, just reach out to me or to Philip, who was said to be the speaker today. He unfortunately couldn't manage, but I filled him. But yeah, you can contact whoever you want from us both. We will answer as soon as possible.
Great, thanks, Kai. So we have a few questions for you here. First of all, what battery/DC bus voltages does Jungheinrich use in its different machines currently and in the future?
So we are currently in this, let's say, low voltage range, meaning for our forklift trucks, we are using starting from 24 volts up to 80 volts lead acid. And for our powertrain solutions department, we are working on 48 volt and 96 volt. For most people here, 48 volt is still low voltage, and then at least for off-highway machines, there is some kind of border at 75 volts. So 96 volt might sound as high voltage already to you, but depending on which kind of machine you build, for example, a telehandler, if it's governed under the forklift law, then 96 volt is also still low voltage. But the answer is 48 volt, 96 volt.
Great. Next question. How are you transmitting safety critical data over CAN bus, emergency stop signals, etc.?
Yeah. This depends on the machine and the layout of the machine. If, for example, we have also the main, let's say, let's go back a bit here. Oh, sorry. If we also have the this is a bit laggy. If we also have the master controller, now it's working. If we also have the master controller, then we're working with a safety controller with more than one core to have, for example, fallout safe signals. If it is an emergency stop, for example, you can break open an electric circuit, and then you have transmitting a signal with performance level C, for example. This is also how we communicate between our central BMS unit and then the lithium-ion modules. If we want to open the contactors, we then have a performance level C CAN signal, which then opens the contactors and also checks if the contactors are really open, and then communicate back. So that is a fallback loop. So this really depends on, as I said, on the system architecture and how much of the integration is done with us and with our components, really. Yeah.
Do you foresee more standardization of control interfaces on the horizon, such that the risk of handpicking is eventually reduced?
Well, that would be great. I think the best example really is the charging plug. We are now looking at more and more Type 2 charging interfaces, and um, before, for example, for the forklift trucks, when they started, there were also different variants of charging plugs, and then also you need to have, if you had different forklift truck suppliers or forklift truck brands in your warehouse, you need to have different chargers from different suppliers, to which then had one specific plug. And now it's only one plug that is left, because this was standardized, and that makes life much easier for everybody. And we truly hope that this also happens within the general electrification, but also especially for off-highway machines, because this would decrease complexity. But still, even if you have the same plug on each component, the pinning might be completely different, and also the CAN messages might be completely different. So it will not completely reduce the complexity, but we do also think that there will be standardization, definitely, and there must be, because otherwise it's not to handle for anybody. Yeah.
Okay. What safety level is required to be achieved in an electric forklift?
In an electric forklift. So as I said, I think this depends on the function and the severity of a malfunction of this function. Sounds a bit strange, but I think this is correct. And for the batteries, usually it's performance level C. I have also seen safety functions performance level B, but for the most critical ones, we are working on performance level C. Yes. Yeah.
So Jungheinrich is clearly using products coming from material handling applications. Is intention of Jungheinrich to develop products more in line with construction equipment or agriculture markets where ambient conditions are more severe?
Mm-hmm. Yeah, this is a very good question, and we get asked that quite often. Let me jump back here. So the general assumption is that a forklift truck is working in a very safe environment in a warehouse, driving on smooth ground and lifting pallets from A to B. The reality is that, speaking of mechanical requirements, for example, the forklift trucks do not have any kind of suspension. They have usually some kind of hard rubber wheels, and the warehouse doesn't always look as good as the warehouses in Europe. And every little crack within the floor leads to a high impact, a high shock on the whole machine. So we are measuring up to 30 or 40 Gs at cell poles within the battery in daily use within forklift trucks. So in terms of mechanical robustness, for example, all components are IP67 or higher. They withstand mechanical shocks, as I said, up to 30 Gs or even higher. Also vibration. So what I want to say is, a forklift truck, the life is not as easy as it might look from the outside, but it's correct that the requirements of the off-highway machines are a bit, or differ to some extent. And this is what we also, or why we also adjusted our components a bit. So every new component that is developed within the Jungheinrich group does also get our influence and our specifications, so that it has to comply to our powertrain specifications as well. For example, the battery here with the IP67. And we do also develop our own components on our own, but also with suppliers that are then specifically built for the off-highway or off-road market, and or construction agricultural machine. And this is usually then with higher ceiling, more common, let's say, more common plugs, and also with, maybe that's important to note, also only air cooled, because we have seen that this also reduces the complexity of an overall system. So we try to really reach these three goals there. Yeah.
Great. So we're just going to tackle a couple more here, then
Yes,
we'll wrap it up.
sure.
So what is the ratio of autonomous to non-autonomous e-forklifts at Jungheinrich, and how will this ratio look like in 2030?
Well, predictions are difficult, especially if they are looking into the future, right? The autonomous section is increasing a lot, but the manual driven, let's say, or non-autonomous section is way bigger still. So we are really at the early stages there, and it depends also if it's for example, a machine or a vehicle that is working in a safe space, for example, in some kind of warehouse where you have to just, so to say, just push boxes upwards and then get boxes from a different shelf when no people are around. This is really accelerating, and there we are selling autonomous vehicles for or machines for a lot of time now. But it gets difficult when you have people running around, when you have machines working in the same area as all the other logistic people within the company. I can't really tell you the exact share, to be honest. I know that there's a lot going on, not only at our company but also in the whole industry. But really, until it works with people in an, let's say, unsafe space, uncontrolled area within a warehouse where everything is going on, this is not as easy.
Great. I think we'll wrap up with this last one. And so
Sure.
just a reminder, if anybody else has any more questions, please get in contact with Kai or Philip directly. So last question here. When designing for your fully integrated powertrain systems, do you prefer to develop with integrated components with multiple functions or independent discrete components?
Mm, This also depends a bit on the component we are talking about. We, for example, with the chargers here that we have developed with a supplier, we have also tried to not only charge but also have a bidirectional feature, so to really like ramp up the features within the components. But and also to include, for example, for 96-volt batteries, to include a pre-charge circuit in there, to include dual pole braking already within the battery, to lower the complexity of the rest of the system that you need to integrate. But we usually try to get the main function, the core function of the component as good as possible. And then if there's a chance to lower the complexity of the whole system by also getting some more functions within this component, we do that. If we don't see a benefit for the customer in terms of integration, not really. And then keep therefore the cost of the component as low as possible, because then we have a standardized product which has one or two core functions. This can exactly do what it needs to do, can do that very well, and do that on a low cost level. And this is usually a deal breaker. Yeah.
Okay. Thanks to everybody for attending the session, and Kai for such a great presentation and your ability to answer those questions. For everybody else, please join the next session from the lobby. We'll be here with more.